Welcome to my channel. This is Magesh Kumar. In this channel, we are continuously uploading videos related to chemistry and giving solutions to various competitive examinations like TRB, CSIR, GATE, JAM, etc. So in the previous video, we have uploaded TRB Assistant Professor 2016 Nuclear Chemistry area. This video includes coordination chemistry part. Here, total number of 8 questions have been asked. The 8 questions have come under the 4 concepts. So the questions are merged related to the concept. In the upcoming videos, we will upload solution to the other topics. Okay. So I hope that this video is helpful to you. If so, you may subscribe it to empower us. We expect your valuable comments to improve this channel. Let us move to the video. The ground state energy term for D1 and D9 free metal ion is various options are given. So what is the concept? The term symbol is in the form of L2S plus 1 and J. Here the S is the total spin quantum number. So it is the sum of all spin quantum number. And the L is the total orbital quantum number. And J is the total angular quantum number. So this is a general format. Here the D1 configuration, it has 1 electron. The orbital quantum numbers are plus 2, plus 1, 0, minus 1, minus 2. The S is plus of, and so the spin multiplicity 2s plus 1 is equal to 2 into of plus 1 is equal to 2. And the L is equal to plus 2. Here L is equal to 0, it means it is S. L is equal to 1, it is P. L is equal to 2, it is D. And L is equal to 3, F, and so on. So L is equal to plus 2, so the term is D. And J is equal to L plus S to L minus S. Here only 1 electron is there and it is less than half filled. If the electronic configuration is less than half filled, we have to account the L minus S value. If it is greater than half filled, we have to account L plus S value. So it is 1. Now L plus is equal to 2, L is 2 and S is half and 2 minus half. Here it is taken. So what's the term? The L is D. L is D. And 2s plus 1 is 2 and here 3 by 2, 1 and half. So this is the term symbol. So the problem F4, F3, C, D2, D5. It is correct. Here without calculation we can answer this question by means of spin multiplicity. Spin multiplicity. D1, so the spin multiplicity will be 2. So any other option has not the value 2. So without calculation the answer is 2. Term symbols includes the J value. The terms is, here the J is not included. Okay. And in this term symbol there is a generalization. One is the closed configuration. Closed configuration, that is D10, P6, etc. The term symbol is S10 because the L and S values are 0. Okay. And in the second generalization, Dn and D10 minus n having the same electronic configuration, same arrangement. So the tram symbols are same. Okay, so the generalization. So here the D1 and D9 has the same arrangement. So the tram symbol is same, D2. Next question. The correct order of spectrochemical series is, what is spectrochemical series? It is the increasing order of ligands in splitting the d orbital, splitting the energy of the d orbitals in octahedral complex. So the weak ligands followed by the strong ligand. Weak ligands are followed by strong ligands. Okay. So the spectrochemical series, the ligands are arranged by the increasing order of splitting the energy of d orbitals. Okay, so this is order. So the spectrochemical series starts with iodine in I, bromine. I brought some SCN, colorful Cl, sweets for home H2O, containing C2O4 2 minus, water H2O. So here only H2 is there. Okay, so it is OH containing water. Nuts, what is NCS, nuts. Then essence EDTA. Okay, along with, that is ammonia, egg EN, and canned CN, coke CO. So it is a mnemonic to remember the spectrochemical series. I brought some colorful sweets for home containing water, nuts, essence along with egg, canned coke. Okay, here, so what are weak ligands and what are strong ligands? So weak ligands having the donor atoms in general halogen, oxygen, sulfur, and strong ligands having the donor atom nitrogen, carbon, phosphorus. So weak ligands generally having halogen, oxygen, sulfur. So in problem the arrangement is, so in A option the carbon ligands with the cyanide is given as weak ligand and OH is stronger, so option A is wrong. In B, here carbon and halogen, so in the order, so it is your answer. Here what is wrong? The CN is in the middle after halogen and followed by oxygen, so it is wrong. Here iodide is given as strong ligand and the cyanide is a weak ligand, so it is wrong one, correct one. So you have to remember. Next question, pick out the incorrect statements. Potassium ferrocyanide is less stable than this one. How can we find out the answer? So what is the concept? Regarding stability, we have to find out the central metal ion and the ligands. In case of central metal ion, the charge increases, stability increases. And electronegativity of the central metal atom increases, stability increases. And the size increases, stability decreases. So central metal ion in general it is a Lewis acid. So for Lewis acid, so the accepting tendency increases, the stability also increases. Regarding ligands, the more basic ligands, it is more stable. So basic nature increases, stability increases. That is the donating tendency of the ligands will increases. And chelation, so polydendrite ligands. So chelating increases, stability increases. So regarding size, there is a Irwin-Williams series. Irwin series. What is that? So the first Stanson series, the MS2 plus, Fe2 plus, cobalt 2 plus, nickel 2 plus, and copper 2 plus, and zinc 2 plus. So this is a Irwin-Williams series. Okay, now consider the question. So here the first option, the potassium ferrocyanide is less stable than K3FeCN6. Here the oxidation number of ion is 2, oxidation number of ion is 3. So charge or oxidation number increases, stability increases. So which is the ferrocyanide is more stable than ferrocyanide. So it is less stable and it is more stable. So it is a correct statement. And second one, in metal complexes the ligands are different. We know that amine, it is more basic than this one. So more basic, stability higher. So amine is more stable. So it is correct. The third one, En2 is a polydentate, bidentate ligands. Amine is a monodentate. So it is more stable, but it is given less stable. So it is incorrect statement. And in the fourth one, charge. The charge of the cobalt, and here the charge of the cobalt. It is +2, and here it is +3. Okay. So it is more stable, but it is given it is less stable. So it is incorrect statement. So the incorrect statements are 3 and 4. Next question. Match the following. The various complexes given, electronic configuration and the ligand nature is given. So first one, the zinc complex, the oxidation state of zinc +2, D10, T2G6, Eg4, and it is a closed configuration, that is CFS is equal to 0. So it may be weak or strong. And next one, nickel complexes. Here the nickel is in +2 state, D8 configuration. The fluorine is a weak ligands. So the ligands with the donor atom halogen, oxygen, sulfur are weak. So it is weak, electronic configuration T2G6, Eg2. And cobalt complex. In cobalt complexes, the charge of the cobalt is 3. So it is D6 system. D6. So it will be T2G6, Eg0. Why? Because amine is a strong ligand. So low spin complexes. So it is strong. So how to match the question? Zinc is configuration is T2G6 and Eg4. The first one A. First one A. So there are two options are there. For first it is A. So D and A is not the answer. So we can neglect this. And zinc is strong and weak. So second is given. So in both the cases, second options are given. Then compare your nickel. Nickel is a D8 configuration. So it is 2 Eg6, Eg2. So C is the correct answer. And strong bases. Okay. So your option is C.